Let's find the volume of the solid bounded by the xy plane, the surface z equals x squared plus y squared plus 3, and within the cylinder, x squared plus y squared equals 1. Let's do our best to sketch a 3D graph of this. The surface z equals x squared plus y squared plus 3 is an elliptic paraboloid. The vertex is at 3 on the z-axis, and it is a parabola that opens up. And then the cylinder x squared plus y squared equals 1 can be drawn as a circle in the xy plane, and then that vertical cylinder here is found. So we want to find the volume of this region. Kind of looks like a cylinder with a bowl scooped out of it. And the base region would be this portion in the xy plane. So to find the volume of a solid, if you're given a function of x and y, we can say the volume can be found using a double integral where r is that base region and f of xy times differential area. Now in this case, our base region is a circle, and the height of this function is given by this z equals x squared plus y squared plus 3. So let's sketch the base in 2 dimensions and determine the bounds of integration, since this is in the section of polar coordinates, and we're looking at this x squared plus y squared is equal to 1. You know that that is a circle. This is our base region here. And we can determine the bounds of integration. We can either draw vertical rectangles or horizontal rectangles if we wanted to use dy dx or dx dy. But since we're practicing the polar conversion, we can slice this like a pie and use the r, find the bounds for r and theta. So if we slice it like a pie here, this little portion here is your d theta and this is your dr, and the bounds for your radius would be from your inside radius of 0 to the outside radius, which is the point on the circle with the radius of 1, and then your smallest angle, theta, would equal 0, and then the largest angle, theta, would equal 2 pi. That would give you the complete circle. So let's go ahead and write this double integral r, where our function of x and y is x squared plus y squared plus 3, all of that times your differential area. When we convert to polar, we're going to use r's and thetas for our differentials, and we're going to make the conversion inside the integral as well. So this becomes x squared plus y squared is converted to r squared plus 3, and our dA, we can write this as r times dr times d theta, or r times d theta times dr, since they're all constant here, where the inside bounds for r go from 0 to 1, and the outside bounds for theta go from 0 to 2 pi. Okay, now if we distribute that r, we can then evaluate that inside integral. So this would be r to the third plus 3r dr d theta. Now when you do the inside integral, it's in terms of r. You treat r as a variable and treat theta as a constant. When you integrate that, you get the integral from 0 to 2 pi of the antiderivative of r cubed. It's going to be r to the fourth over 4 plus the antiderivative. The antiderivative of 3r is going to be plus 3r squared over 2. And you're going to evaluate that for r equals 0 to r equals 1, and then your d theta. When you plug in 1, you get 1/4 plus 3/2. which is 7 over 4. You get the integral from 0 to 2 pi of 7 over 4. And then when you plug in 0, you get 0. So it's going to be 7 over 4 d theta. Now the antiderivative of 7 over 4 d theta, since 7 over 4 is a constant, that antiderivative is going to be your oops, it's going to be 7 over 4 times theta, where theta goes from 0 to 2 pi. You're going to plug in 2 pi, so you get 7 over 4 times 2 pi, minus what you get when you plug in 0, which is 0. And that simplifies to 7 over 2 pi. So the volume of this region that is bounded by that paraboloid and that cylinder and the xy plane is 7 over 2 pi cubic units.